This presentation is entitled Graph Queries in a Relational Database Management System. Now it turns out relational databases are good for doing queries on things like flat lists. They're not so good for doing more sophisticated kind of queries. For example, what are called inference queries. Typically, to do those class of queries, you have to employ the use of knowledge management technology. For example, Stanford's Protégé system is able to do those kind of queries. Now, unfortunately, most data today is stored in relational database systems. So an ideal solution is to somehow come up with a way of doing sophisticated inference kind of queries using relational technology. This is what this presentation covers today.
Graph queries in a relational database management system. Information technology has a number of significant challenges associated with it. In today's presentation, we're going to look at queryability, the inability to easily navigate complex structures. To address the challenge identified on the previous slide, we're going to look at a technology called TCSQL. In particular, we're going to look at a capability that provides sophisticated query capability using standard relational database technology. We will look at a variety of query types. We're going to start by doing a little graph theory here. In front of us are two graphs, a family tree and a graph of bus routes. Some of the components of a graph consist of the following: the notion of something called nodes. In this family tree graph, the nodes happen to be the names of people here. A second component of graphs are these things called connections here, or edges. And they happen to be the arrows we see between nodes here. Sometimes in graphs, you have a semantic relationship associated with these arrows. In this family tree graph, we have a father of relationship and we have a mother of relationship. Sometimes with graphs, you have scalar values associated with the connections. In this bus routes example, the scalar value represents a cost of going from one city to another. The notion of transitive closure is a concept that is foreign to most people. So let's look at a definition of transitive closure. Given a graph G, the transitive closure of a graph is the set of all potential paths between all nodes in the graph here. So in fact, the transitive closure of a graph can be represented using a relational table here. So the way to think of the population of this table, you can think of it as follows. Take any two nodes in the graph, let's say starting with N1 and looking at N6. Does there exist a path, directed path from N1 to N6? The answer is yes. Therefore, we see a transitive closure record here. Does there exist a directed path from N2 to N6? Notice I say the word directed, you got to follow the directions of the arrows. The answer is no. So N2, N6 does not show up here. So what can you do with the transitive closure of a graph? You can use it to navigate a graph. So if we want to know all of the descendants of N1, what we can do is write a select statement as follows. Select child from transitive closure where parent equal N1. Now let's play computer a second here and let's execute this query here. Let's find all the rows here where the parent has a value of N1. We see that in green here. And let's find all of the children from all those records. And what we find is we get N2, N3, N4, and 5, N6. So in fact, that represents all of the descendants of N1 here. Now, one of the unique things about transitive closure with respect to TCSQL features the ability to maintain transitive closure in a graph as a graph changes. So normally, if you're adding or deleting nodes or connections in the graph, what happens is you typically have to rederive the transitive closure from scratch. One of the features of TCSQL is its ability to maintain transitive closure whenever nodes or connections are added or deleted from a graph. The object-oriented paradigm can be represented as a graph problem. So here we have a class here called class 1, which has properties A, B, and C, and a hazard relationship between the class definition and its associated properties. We also have another class here called class 1.1 with properties D and E. And we see a relationship here between these two nodes, an is-a relationship, meaning that class 1.1 is a specialization of class 1. Now let's look at a graph here. Let's look at what happens if we want to instantiate class 1.1. Let's look at the equivalent object graph. In this case, it would look like the following. Assuming we want to instantiate class 1.1 and we're going to call that object 1, what happens is the following. We first want to instantiate properties D and E, and then we want to look at this inheritance is a link here to inherit properties A, B, and C, which is what you see down here. Okay, now let's look at the relational tables needed to support this paradigm here. So we have the notion of a class table here, which represents the nodes of our class graph here. It's basically a name-value pair here, and we have a type column here, and legal type values. This represents basic class types here. We have a class connection table of parent-child nodes here, and a connection type here. In this case, it's going to be either has-a or is-a. And then we have a transitive closure table representing the transitive closure of this class graph. And assume for a minute that this transitive closure table is automatically populated and managed whenever nodes or connections are added or deleted in this class graph. Let's look at the tables needed to support our object graph here. We have a table called object, which represents the nodes of our object graph here. Again, it is basically a name-value pair with a class column here representing the kind of class that we're instantiating here, including the class properties. We also have an object connection table here, which represents the connections of our object graph. So it's a parent-child pair, again with connection type. And we have a transitive closure table associated with our object graph. And assume here also that this transitive closure table is maintained automatically whenever nodes or connections are added or deleted in our object graph here. So this whole paradigm here I'm describing here with these 6 relational database tables is something known as a soft schema. In the last slide, we looked at the notion of something called a soft schema and the 6 relational database tables associated with it. In this slide, we're going to look at a query which utilizes a soft schema and does a join to conventional relational tables like you see here. In this example, we're going to do the following query. Find all diabetes patients here. So at the top here, we have a graph, something called an ontology, where you have a semantic relationship between nodes here. In this case, it's an is-a relationship here. At the bottom, we have a standard relational table, an electronic healthcare record table here with patient information. And so the query looks like the following select statement here. And what we're going to do is we're going to play computer and run through step by step what happens in executing this query. In the first part here, we have a where transitive closure patient is diabetes. So we show that here. And what we're going to do is look at all of the children, in other words, all the descendants in the transitive closure table here. So that shows up in purple here, all the descendants of diabetes. And then what we're going to do is a join on the electronic healthcare record table here, where the fact value corresponds to the descendant value here of the transitive closure. And then we're going to return here the select e.patient. We're going to return the patient column information here in the result here. Now this query is an example of a query type called a subsumption query. For the next query example, we're going to use an ontology called SNOMED CT. It's a medical ontology containing roughly 400,000 vocabulary terms associated with healthcare here. So you see a picture of it here. Now the SNOMED hierarchy isn't really a single hierarchy, it's called a polyhierarchy, or a directed acyclic graph, meaning that for a given node you may potentially have multiple parents associated with it here. So here in this close-up view of a portion of SNOMED, we see this notion of clinical finding here and a bunch of descendants here, and we see at the bottom here something called acute heart disease. And we see that there's multiple paths going from clinical finding to acute heart disease. In this query example, what we're going to do is the following. We have 2 nodes here, clinical finding and acute heart disease. And what we want to return is the actual path all the intermediate nodes between clinical finding and acute heart disease that we saw on the previous slide. And so we're going to do a select statement here. In this case, we're querying from something called object path. It's actually a view definition that combines copies of the transitive closure table. I'm not going to bother showing the details of the view definition, but merely to show that by using the transitive closure table, it's possible to return all the intermediate nodes. And this kind of query is referred to as a path query. Let's look at another query type example. We have a graph here representing an object breakdown structure here. So we have an organization broken down into various departments here. We see a legend here, so we see the relationship between nodes here is OBS, organization breakdown structure. In support of this graph, we have two tables here, a transitive closure table of the graph and a table representing a collection of people associated with each department number here. We have another graph here called a work breakdown structured class graph here. So this is representing a template for a project plan. So projects are broken down into one or more features. Features are broken down into hardware and software units. And we see a feature has a property here called customer. We see a small feature and large feature are both specializations of this general thing called a feature. Small feature and large feature each have their own properties here. We see a feature also is broken down into hardware and software units. Those have properties of firmware and NCSL respectively. NCSL stands for non-commented source lines. And we see NCSL is a special instance, a special name for a more general term called lines. We have a couple tables associated with this graph, a class table representing the nodes here and a transitive closure table of this graph. And we have another table here, a WBS instance graph, meaning that this represents an instance of this class graph here. We have a couple projects here, P1 and P2, broken down into small features and large features, broken down into software and hardware units. We have a number of properties associated with these entities down here. Okay, we have a couple of relational tables associated with this graph. We have an object table representing the nodes of this graph and a transitive closure table representing the transitive closure of this particular graph here. And the query we want to perform is the following. Imagine you're the manager of a department up here, organization 553. And what you want to know is you want to know all of the features your people worked on and the total number of lines they contributed for each of those features here. Now, if you think about this, this is a very complex kind of example. It requires the traversal of all three of these graphs here, the object instance graph, the class graph, and the work breakdown structure instance graph here. It would be something very, very complicated. Rather than show you a complex select statement here, doing a join of the associated tables with each of these graphs here, what I'm going to show you instead is a select statement that utilizes a view definition that hides all of the detail here. And so what we see is select star from organization contributions, where the organization name is 553, where something called a superclass is this notion of a feature, and superclass property is lines. We want to know how many lines for each feature for the people working in organization 553. Now, the interesting thing about this query is the following. Let's say tomorrow that someone decides to change this class definition here, decides to introduce something called a very large feature. What would we have to do to this query to incorporate the notion of a very large feature? The answer is nothing. This query does not need to change at all. What if tomorrow someone decided that, well, in terms of lines, we also want to call firmware a kind of lines also? What do we need to do to this query to incorporate that kind of logic? And the answer is absolutely nothing. The only thing we need to do is, in fact, put a connection between the notion of firmware and lines to indicate that firmware is a kind of lines here. This type of query is what's called a polymorphic query. And the beauty of this kind of query is it allows you to make changes here and never have to make modifications to the original queries at all. Let's look at another query type example. In this example, we have a graph here representing a project management system here. And so we have an ABS relationship here, which stands for application breakdown structure. So we have this application broken down into various subsystems here. And imagine we have two candidates for a job here, okay? We have a person that worked on this tracking subsystem for 4 years and this report subsystem for 6 years. And the particular job in question is the following. We want to know which of these candidates is better suited to write Pascal code here. And what we've done with this application graph is we've overlaid it with this semantic network here, this ontology that categorizes the various subsystems here. So tracking subsystem consists of Ingress database technology, code written in SQL and code written in C. This reporting subsystem is just code written in SQL. So looking at these two candidates, which is the better, more suited candidate to write Pascal code? And it turns out the answer is the tracking subsystem person here. Why? Because of the following. Although you're looking for someone with direct Pascal experience, what you end up doing is the following. You see that both Pascal and C are special cases of this more general category called procedural programming languages. And this person does have C programming experience here. And so you can infer that if they could do C, they could probably do Pascal programming. The last slide depicted a query where you're trying to match the most qualified candidate for the particular job in question here. So now we see an actual select statement here, and rather than showing the underlying relational database soft schema tables that were used, we encapsulated the complexity in a view called desired skill here. In this particular example, we're trying to find someone who has both Java and Oracle experience. And we're willing to abstract one level of abstraction, meaning that if we can't find someone with direct Java or Oracle experience, we're willing to go up one level of abstraction to find the next best thing here. And so we see in our results here, we see this person named Paul here, and the skill we're looking for is Java. In this case, they actually have Java experience, so we didn't have to abstract at all. In this other case, the same person, Paul, has C++ experience. Okay, the desired skill is Java, and so we had to abstract one level of abstraction, the common skill being object-oriented programming languages in general. So you get the idea here. And so what this query type is called is an inference query. Let's look at another query type example. In this query, we're going to do the following. We want to find all patients in an electronic healthcare record system having autoimmune diseases of the digestive system. And the query we're going to look at is the following here. Select various columns from this thing called ontology, doing a join on an electronic healthcare record table here. Now this ontology thing here is really a user-defined function. Rather than showing you all of the joining to the soft schema tables I talked about earlier, what instead I'm going to do is show you the underlying algorithm implemented by this user-defined function here, which is the following. So this function takes two parameters here, and the first step in this algorithm is to use natural language processing to find all ontology concepts associated with autoimmune diseases. I should mention that we're using the SNOMED ontology I mentioned earlier, which has approximately 400,000 vocabulary terms associated in the healthcare field. So what we're trying to find is those SNOMED vocabulary terms closely associated to autoimmune disease. We're also going to use natural language processing to find those SNOMED terms associated with this notion of digestive system here. We're then going to find the descendants of step 1 here and the descendants of step 2 here. And finally, we're going to find all the concepts related to the concepts returned in steps 3 and 4 here. And finally, we're going to do a join on the electronic healthcare record table, the patients having the diagnosis listed in step 5 here. Now this is very, very complicated, but we're able to easily encapsulate it into a user-defined function here. And this kind of query I call a multi-dimensional relationship query. Let's look at another query type example. In this example, what we want to do is find all ontology concepts related to this thing called diabetes mellitus. Okay, so now we're going to demonstrate a SQL stored procedure that was created here. I'm not going to show you the internals here, but it takes one parameter. So we're going to pass in this notion of diabetes mellitus. And what is returned is the following. So you pass in diabetes here, and what you get are all of the synonyms and specializations associated with diabetes here, over 3,900, associated diseases or syndromes, medical devices, genes or genomes, body parts, so on and so forth. So what you're able to do is from a single classification here, find a whole bunch of related classifications to diabetes. And this kind of query I call a related ontology concepts query. So why is all of this valuable? First of all, it demonstrates an ability to perform rather sophisticated and powerful capabilities typically found in a knowledge management system. Secondly, it demonstrates the power of natural language processing to ontologically categorize any random text here.